So this is the capture-recapture method. I want you to imagine that we've got a large lake and there are some fish that live in this lake, but I don't know how many fish live in the lake. So it's not just 7. I've just tried to represent there are some fish in the lake. Now what I would like to know is how many fish live in the lake. Now it will be very difficult to capture all of them and count them, so I'm going to use a slightly different method, and I'll take you through the procedure. Now I start by capturing some. It doesn't actually matter how many, but I'm going to capture, say, 60. So on day 1, maybe I set up a trap or something and I capture 60 of them. Capture 60 of the fish. Okay, that really could be any number, but I'm going to do this with 60. What I'm then going to do is mark them somehow. So I'll put a piece of dye on them, like a purple marker or something on their fins. So capture 60 of them and now mark them. And imagine I've done that with like a purple marker pen or something. So I've coloured in their tail fin or something like that. And I now release them back into the lake. All right. I then wait a day or so, and the next time I want to do some maths, I capture another sample. And again, it doesn't matter how many, but let's do it with the number 40. So suppose I capture 40 fish for the second time. And let's suppose that when I look at the 40 fish that I've captured, 5 of them are marked. 5 of these have my purple tail fin, right? 5 of these are marked. This is actually enough information to estimate the total number of fish in the pond. It doesn't work it out exactly, but it does actually surprisingly most of the time give a really good estimate. And here's how it works. We note that in our second sample, 5 out of 40 had tags. Sorry, not tags, sorry, 5 out of 40 were marked, with the purple dye. And the assumption is that when I release them, they all mixed up randomly again. And so my assumption is that this proportion of fish in my second sample that has tags is the same as the proportion of fish in the first sample. And my first sample was 60 out of the mystery population. So I'll say that again slowly. I'm trying to work out the number of fish that are in this lake. I don't know how many are in there, so let's call it X. So the population of fish in the lake is X. It's a mystery number, don't know how many fish there are. And on the first day, I mark 60 out of all of them. So 60 out of all of the fish I cover in purple dye. And then a day later, once they've all mixed up again, I do a new capture. 5 out of the 40 that I capture in my second sample, they are marked in dye. And my assumption is if they all mixed up appropriately randomly, then these proportions are the same. The proportion that are marked in the first sample is the same as the proportion which are marked in the second sample. And now you've got quite a few ways you could finish this off. You might notice, for example, that the bottom number is 8 times bigger than the top number. So 1/8 of your sample is marked. So you could times this by 8, and that would give you the X. You might notice that to get from here to here, you multiply by 12. And so you could do the same. You can multiply this by 12 to get the answer here. So either of those would work. However, if the numbers are really weird, so, on the first day you only managed to capture 57, and then the next day you captured 32 of them, and 3 of them had, if the numbers are really, really strange, then you might not notice such nice things about the numbers. So it was easy to see that to get from here to here times by 12, you could do the same here. It was easy to see that from here to here it's times by 8, you could do the same here, but unfortunately it's not always going to be quite that simple if the numbers are really random. So I'll proceed with a method which will always work. How do I figure out X? Well, what I'm going to do is I'm going to flip both sides over. So this currently says 5 out of 40. I'm going to turn it into 40 over 5, and this says 6 out of x. I'm going to call that x out of 60. So flip both sides over, and that's allowed because you're doing the same to both sides. And now to get x on its own, I just need to multiply both sides by 60. Right, so times this by 60, you just get x, and times all of this by 60 is whatever it is. And I'm going to do that on a calculator. So that is 40 over 5 multiplied by 60, and it gives me the answer 480. 480 is my estimate for how many fish are living in this lake. Notice that you could have got that the other way. If you notice the nice relationships between the numbers, I said that to get from here to here it was times by 12, and indeed if you times 40 by 12 you do get 480. I also said notice that to get from the top number to the bottom number it's times by 8, and that works again, doesn't it? 60 times by 8 does indeed give you 480 as well. So any of these methods work, but I'm recommending this approach where you write it as fractions, then you flip the fractions over, and then you times by whatever x is being divided by. This method will always work no matter how weird these numbers are. It's perfectly possible that the answer you get here is some weird decimal, but then you just round it appropriately based on the question. Now, you're often asked to state any assumptions that you've made in the process, and I've already explained one of them. My assumption is that they all, when I release them, they all mixed up again randomly. That's important because if they didn't all mix up, then maybe by coincidence all the fish that I marked on day 1 are all still sort of clustered together, and then I'm likely to have overestimated here the number, or possibly underestimated actually, what I've got over here. So I need it to be sort of a random sample, because otherwise you could say, well, of course you've got the same fish that you got last time if they didn't all mix up, right? There are a few more practical things that you're allowed to say to score the mark. So things like, I had to assume that the purple mark I put on the tail fin didn't rub off or didn't wash off. I need to assume that between the 2 days that no new fish were born and no fish died as a result. I need to assume that the fish were just as likely to be caught the second time as they were the first time, and that they're not suddenly scared of being caught, because if they suddenly realise that when they get caught they get purple dye on their tails, they might be less inclined to come near my net or whatever it is I'm using to capture them the first time. So there's lots of practical things you can say, like no new births, no deaths, no harm has come to them, nothing like the mark has come off. But what they're really expecting you to say there is that when you release them, they all mixed up randomly, and both samples are sort of fair and representative. So here's another example, same idea again, but just got a lot more words going on. So previously I was taking you through the method from beginning to end, but now it's a specific question that I'm trying to answer. So we've got this person, the scientist, and she has captured 150 seagulls. She puts a foot ring on them. You may have seen those before on birds. They're like little metal rings, and they go around, well, they're sort of above the leg really, but they're called foot rings. And then she releases the seagulls back into the wild. The following day she tries to capture some more seagulls, and she only manages to get 80 this time, and she notices that 8 of those already have her foot rings on there. That's enough information to work out how many seagulls there are in the whole population. So what we need to do is think about the proportion of seagulls which are tagged with these foot rings in both samples. So in the first sample, there are a mystery number of seagulls, X seagulls, but she puts tags on 150 of them. She captures 150, puts foot rings on all of them. So that's the proportion, that's the fraction of all of the seagulls that have foot rings. And in her second sample, she only manages to get 80 this time, and 8 of those have foot rings on. So these are equal, is what we're going to say. That's a bit of an assumption. and it's not a terrible assumption so long as they did all mix up randomly. No new seagulls were born, none died, they weren't more averse to being caught the second time, etc., etc. Okay, now you could solve this in a number of different ways. I don't immediately see what you multiply 8 by to get 150, so I haven't got that shortcut available to me this time. But I can see fairly easily to get from the top number to the bottom number. That's just times by 10. In fact, this fraction would simplify to 1/10, wouldn't it? So in that case, I can see that x is 1,500. But let's do the method that we had before. I'm going to go down here now, flip the fractions over, so that is now going to be x out of 150 equals 80 over 8. And now to get x on its own, you need to undo this division by multiplying by 150. So x equals 80 over 8 times by 150. And when you type that in your calculator, it will say 1,500. So that was my, off the edge of the page, that will say 1,500. Okay. Explain any assumptions that you've made in the process. Don't ignore that, it's often worth a mark. That's all the stuff I was saying before. Things like no new seagulls born, none died, that they randomly mixed up for you, so it's a fair representative sample. There's another one here. I could say I need to assume that none of the foot rings fell off, or something like that. Okay, any of those sorts of things are fine.